of graph, DFS. These were the things I guess were taught. So first of all, do you have any questions or doubts on these topics? Hello. I guess you are audible. Acha. Do you guys have any questions or doubts on the topics that were taught in the previous class, like the DFS, BFS, and the what are graphs, the representation of the graphs, adjacency matrix, adjacency list? Any doubts on this? So, like you can write in the chat also, like if you have any doubt, or else we will start with probably 01 BFS or Dijkstra algorithm, because these two algorithms are mostly asked in the interviews. So we can start with those. Okay, so I think we can start with first 01 BFS. So let me share my screen first. Just a minute. So is my tab visible? Like the dog, is the dog visible?
Yes, Bhaiya.
So last day I think you were taught about BFS. So 01 BFS is a modified version of BFS, where there are two types of edges. Like the one type, the first type of edge has weight 0, and the second type of edge has weight 1. Okay, so basically these are the two types of means edges, and we use 01 BFS to find the shortest path from a source to a destination. Okay, so first of all, I guess means you have been taught BFS. So can anyone just recap what BFS is? It means how the algorithm works. Just a quick recap, because the algorithm will be very same here, just with a 2 or 3 line modification. Anyone can say, like,
We
anything.
traverse line by line in BFS,
Okay.
like level order.
Okay, so yeah, so basically if we have a graph like this, so let's say 1, then we have 2, 3, then in the next level we have 4, 5, and 6 and 7. So first in BFS we will traverse 1, then we will traverse 2 and 3, and then we will traverse 4, 5, 6, 7. So what we do, we traverse level order, means level wise in BFS. Okay, so we start from the 0th level, that is 1. We then go to the first level, that is 2 and 3. And then we go to the next level, that is 4, 5, 6, 7. So like this we go on. So can anyone tell what is the limitation of BFS? Means why we have to use 0 1 BFS? Why can't we use normal BFS for finding the shortest path in a graph? Means what are the limitations of BFS? Means the normal BFS. Anyone? Hello. No one. Then means you told you don't have any problems or any doubts. So means why can't we use BFS everywhere? If finding element is too far from root, it takes too much time. No, BFS is the fastest way to find the shortest path. But in every case we can't use BFS. Like for only a specific type of graph we can use BFS. Like what? So what is the limitation of using BFS? So you people know about weighted and unweighted graphs. Hello.
Yes, भैया.
So what are weighted graphs
Every path has some weight in weighted
and what
graphs.
are unweighted?
Don't have weights.
Age have some values, but in unweighted, the age have no values.
Yeah, in weighted graphs, every edge has a distinct weight value, and in unweighted graphs, every weight has a similar value or the same value, right? So
Yes, yes.
the limitation of BFS is that BFS can only be used in unweighted graphs for finding the shortest distance. Okay, BFS can only be used for unweighted graphs for finding the shortest distance. Okay, so this is the limitation of BFS. BFS can't be used for weighted graphs. Why we can't use? I can give you an example. Let's say we have an edge from 1 to 2 and the weight is let's say 10. Okay. Next we have an edge from 1 to 3 and the weight is 1. And another edge we have from 2 to 4. Sorry, another edge we have from 1 to 4 having weight 1, and the last stage is from 4 to 3 having weight 1. Okay, and let's say this weight is 5. Okay, so these are the edges. So what will be the shortest path from 1 to 3? Anyone? What will be the shortest path from 1 to 3?
1 to 4 and 4 to 3.
So what is the weight?
2. 1 plus 1.
2. Okay, so now let's say you are running BFS. Okay, so the graph will look something like this. So in the first level you have 1, in the next level you have 2, 3 and 4. So just a minute, let me draw this. Yeah, so is the drawing board visible? Hello.
Yes, bhaiya.
So you have 1 here, then you have 2, then you have 3, then you have 4, and then you have 4 to 3 another. So this weight is 1, this weight is 1, this is 5, this is 10. Okay. So in BFS, first we will traverse 1, then we will traverse 2, right? And then we will traverse 3. So what is the distance of 3 which will be updated? It will be 5, right? Because when we are traversing 3, the distance will be updated as 5. And next, when we come 3 from 4, we will not update because 3 has already been visited, right? So the distance will be 5 instead of 2. So this is wrong. So are you getting my point? Yes or no? Has everyone got my point or not? Like why BFS will not work for weighted graphs?
Yes, bhaiya.
Yeah, so this is why BFS won't work for weighted graphs. So for weighted graphs, we use Dijkstra. And for weighted graphs, which has only two types of weights, like one of the weights is 0 and the other weight is 1, we use 0 1 BFS. Okay. So first we will look into 0 1 BFS, like what is 0 1 BFS. So let's go back to our doc. So in normal BFS, what do we do? We start at choose a starting point, that is S, and we keep iterating till Q is not empty, right? And we take out the first element in the queue, and then we traverse the neighbors of X. And then we check that whether I is visited or not. If it's visited, then we skip it because it has already been visited. There is no point in visiting it again. Otherwise, we add I to the queue and we continue this process. Okay, so this was normal BFS. Like you put the elements of the first level, then you put the elements of the second level, then you put the elements of the third level, and you go on. So now the only difference between BFS and 0 1 BFS is that uh, you have to change only this line. Okay, so here you check that if weight of the edge I and X is 1, if it's 1, you add I at the end of the queue. Okay, otherwise otherwise if the weight of the edge I and X is 0, you add I to the front of the queue, not end. You add this in the front. Okay, so I am writing a pseudo code here. Okay, like I am writing in simple words, like because many code in C++, many code in Python, so I am writing only the logic here. So if the weight of I is I and X, that means the edge between I and X, if that the weight of that edge is 1, so we add I to the end of the queue. Otherwise, if the weight of the edge between I and X is 0, we add I to the front of the queue. Okay, because just think once, if the edge between I and X is 0, so the distance between so the distance of I and the distance of X will always be equal, right? Yes or no? Hello.
Yes, Bhaiya.
Yeah, so if the
Yes.
weight of the edge between I and X is 0, so the distance of I and the distance of X will always be equal, because the edge weight is 0. So if we traverse that edge, no extra weight will be added. So we add it to the front of the queue, because just after X I will be taken out, because we are taking out uh, elements from the left of the queue, right? So if we add I to the left of the queue, so I will be taken out just after X. So that means so, and the distance of X will be equal to the distance of I, right? So that's why we add I to the front of the queue. Otherwise, if the weight of I and X is 1, we add I to the end of the queue as we do in normal BFS. Because in BFS, if distance I is less than distance J, I is traversed before J. Okay, this is one of the conditions of BFS. If the distance of I is less than the distance of J from the source, I will always be traversed before J. This will always happen when we run a BFS. Okay, so that's what I am saying, that if the edge between I and X is 0, is of 0 weight, so we add Q in the front of I, because distance distance X and distance I will be equal, right? So I will be traversed just after X. Okay, so are you getting my point in this?
Yes, Bhaiya.
Everyone, like, just one is answering.
Yes, yes.
Everyone has got,
Yes,
yeah.
Bhaiya.
Okay.
Yeah.
So this is how 01 BFS works, because uh, if the distance between two elements, if the distance of two elements are equal, they can be traversed one after the other. Because if this condition is true, like let's say if distance I is equal to distance J, J can be traversed just after I, right? So that's what we are doing. We will traverse I just after X in that case, if the weight is 0. And if the weight is 1, we uh, add X to we add I to the end of the queue, and we uh, do as we do in normal BFS, like we keep popping out element from the front of the queue and carry on. So this is 01 BFS. So this is actually the algorithm for 01 BFS. Just you have to change this line, and everything else is the same. So this is 01 BFS, and 01 BFS can be used mostly when there are two types of edges. Okay, like there are the one type of edge has weight A and the other type of edge has weight B. So in these cases, you use 01 BFS, and the time complexity of 01 BFS is the same as the time complexity of BFS. What is the time complexity of BFS? Anyone?
Order of n.
Uh, it's I didn't hear. Can you repeat?
Order of n linear.
Yeah, it's linear. So here also it's linear. Like time complexity and space complexity are linear. So basically, it's not n, it's v plus e, where v is the number of vertices and e is the number of edges. Okay, so that's the time complexity of BFS, and also 01 BFS. Actually, 01 BFS and BFS has the same time and space complexity. Okay, so next we go for Dijkstra algorithm. So means, can anyone tell like what is the limitation of 01 BFS? like just now I told what is the limitation. You should know this. Like, yeah, the weights are limited to 0 and 1. Like if the edges have more than two types of weights, we can't use 0 and BFS. Like if one edge has weight A, the other edge has weight B, and the other edge has weight C. So there are, if there are more than two types of weights, we can't use 0 and BFS. Okay, so in that case we use Dijkstra's algorithm. Okay, so what Dijkstra tells is that means we will, in Dijkstra's algorithm we start traversing the nodes in a greedy manner. Okay, we choose the starting point and select the node which has the smallest distance from the source. Okay, and then from there we select the smallest node which has we select the node which has smallest distance from that node, and we go on like this. So you people know heap or priority queue, right?
Yes, sir.
Yeah. So Dijkstra's algorithm use priority queue or heap for doing this. So what I am telling is that you first take the source, and then you take the node which is closest to x, sorry, to the source, which has means I mean to say which has the smallest distance from source. You take that node x and you traverse its neighbors. So the algorithm will be something like this. You have a priority queue. Let's say the name of the priority queue is, let's say the name is PQ. So you have the source first of all. In firstly you have the source in the priority queue, and then we continue till the length till the size of the priority queue is 0, is not empty. Okay, so now we take out the node which is at the top of the priority queue. Okay, so we take out the top element of the priority queue. We also store the distance. Okay, so distance of source and source with it. Okay, so now we, what we do is that we traverse the neighbors of the node. Anyone wants to tell anything? Okay, so we, what we do is here is that we are traversing the neighbors of the of node, and we check that whether the current distance is greater than the distance of node plus the weight between node and I. So if the distance of I is greater than distance of node plus weight of node and I, so that means that we can have a smaller distance from for I, because we can reach node with a distance of this. And if we go from node to I, so the total distance will be this, right? So the total distance for I will be this, right? So we can have a smaller distance from I than what we have currently, right? Yes or no? So that's why we update distance of I as this, and we push I to the queue, sorry, priority queue. Okay, so this is how it's done. And also like you check here also, like if the node has already been visited previously, so there is no need to visit this again. So this is a wastage of time. So we, if the node has been already been visited, we skip this. So if visited node is true, we continue, or else we mark node as visited, and then we traverse the neighbors of the node, and we check that whether the distance of the neighbors are greater than the, means we check that whether we can achieve a smaller distance for every neighbor or not. And if we can achieve a smaller distance for every means any of the neighbors, we update the distance for that neighbor, and we push that into the priority queue. So this is how it works. And at the end, in the array distance dist, you will have the distance, you will have the smallest distance for every vertex from the source. So any questions on this algorithm, or is everything clear?
Yeah, if we visit the visited array again and again, will it affect something?
I didn't listen you. Can you just speak a bit louder?
If we visit the visited node again, then will it affect or not?
Actually,
If
I
answer
told you
would
that
come correct or not?
when you are visiting a node, you will only visit it once, right? Because here we are checking that if the node is previously visited, we will not visit it again. We will continue. Okay, so you visit the one node only once, right?
Okay, wait.
So basically, I can give an example like how the Dijkstra works. So let's take the previous graph that we used. So you have one, here you have two, here you have three, and here you have four. So this weight is 1, 1, 5, and 10. Okay, so the source is 1. So in the priority queue you have 1. Okay, so now you so the topmost element of the priority queue is 1, and the distance of 1 is 0 because it is the source. So you take out 0 and 1 in the priority queue. Okay, so and here we traverse the neighbors of 1. So what are the neighbors of 1, 2, 3, and 4? So we update. Also the distance array is initialized as infinity for every value. Okay, so the source has a distance of 0 that is initialized, and every other node has a value of infinity, so which means a very large number. So that can be something like 10 to the power 50 or 10 to the power 20, like this. Okay, this is infinity. Okay, so first we have taken out 0 and 1 because it's the only element in the priority queue, so it is at the top. So we now traverse the neighbors of 1. So 2 is a neighbor of 1. So what is the distance of 2 currently in the array? It's infinity. And we will check that distance node plus weight node comma I. So distance node is, so the distance of 1 is 0, and the weight of the edge between 1 and 2 is 10. So 10 is less than infinity, so the distance of 2 will be updated as 10 instead of infinity. Okay, so now we have in the priority queue 10 comma 2. Next we have 3 as a neighbor. So again for 3, the current distance is infinity, and distance of 1 is 0, and the edge between 1 and 3 is 5. So 0 plus 5 is 5, and 5 is less than infinity. So we update distance of 3 as 5. So now we have 5 comma 3 also in the priority queue. Next we have 4. Okay, so 4 has a distance of infinity in the array. So we will calculate as this, like distance of 1 is 0, and the weight of the edge between 1 and 4 is 1. So 1 is less than infinity. So we will add 1, means 4 also in the priority queue with distance 1. Okay. So and also we update here as the distance of 4 as 1. So now we are done with 1. We take out 1. 1 is now popped out, and 1 is the work of 1 is over. Okay. So now we will take the top element of priority queue again. So that is 4. Okay, so now we have 4. So there is only one neighbor of 4, that is 3. So what is the current distance of 3? That is 10. So and if we go to 3 via 4, so what will be the distance of 3? So the distance of 4 is 1. Here the distance of node is 4 here. So the distance of 4 is 1, and the edge between 4 and 3 has weight 1. So the total distance is 1 plus 1, that is 2. Now 2 is less than 5, right? So instead of so we will erase 5 and write 2 here. So the priority queue will be looking something like this: uh, 2 comma 3, 5 comma 3, and 10 comma 2, right?
Yes,
Right. So now there are no more neighbors of 4. So for the work of 4 is over. So now we take again the smallest element of the smallest element in the priority queue, that is 3. Okay, so 3 has neighbor 4, but 4 has already been visited, right? So we have no other unvisited neighbors of 3. Also, like if you calculate the distance of 4 via 3, it will be greater than 1. So 4 is not affected. So the work of 3 is also done, right? So again we take out this. So 3 has already been visited in this case when he calculated for this one. So 3 has already been visited. So we take out this. There is no other work for this. Now we have 2. Okay. So there are no other neighbors of 2. So there is one neighbor of 2. Sorry. Let's say there are one neighbor of 2. That is 1. Okay. So what is the distance of 1? Distance of 1 is 0. So if we calculate the distance of 2, distance of 1 via 2, so it will be distance of 2 plus the edge between 1 and 2, that is 10 plus 10, 20. So 20 is greater than 0. So we will not update the value of 1, and we will also not add 1 in the queue. So there are no other neighbors of 2. So the work of 2 is also done, and the priority queue now becomes empty, and the algorithm is over. So the distance array is finalized. So distance 1 is 0, distance 2 is 10, distance 3 is 2, and distance 4 is 1. So if we check manually also, the distances are all same. Like for 2 the smallest distance is 10, for 4 it's 1, and for 3 it's 2, 1 to 4, and then from 4 to 3. So is this clear?
yes, Bhaiya.
So now can anyone tell what is the limitation of Dijkstra?
We are checking every neighbor.
Means so in which case Dijkstra won't work. Okay, so Dijkstra doesn't work when the weight of an edge is negative. Okay, so like here we have edge weights 10, 5, 1 and 1. So if the weights of the edge is negative, let's say -2 or -3, then in that cases Dijkstra doesn't work. Okay, so the reason why it doesn't work is that because here we are choosing the element which is currently having the smallest distance, right? For example, here we choose 4 because it had the smallest distance from 1. So if we have negative edges, this might not work because if one edge has a negative weight, so the current smallest so the node having the current smallest distance will always not have the smallest distance because for example, let's say if we take this graph, this is 1, this is 2 and this has a weight of -5. Okay, so what will be the distance? Final distance of 1 is 0. Sorry, yeah, the final distance of 1 is -2, right? Because you can go from 1 3. Okay, not, let's not take this. This has a negative cycle. Right, yeah, let's take this one. This has weight. This has weight 1. This has weight 2. Uh, let's see, 3, 2, and 2. Okay. So weight of 1 is 0 and weight of 2 is also 0. You go to 3 and go to 2 and weight of 3 is 1, right? You go from 1 then 3, means 1 to 2 and then 3. So this path has a weight of 1 and the weight of 2 is 0. You go from 1 to 3 and then to 2 and weight of 1 is 0, right? So in this case, if we run Dijkstra, we will first select 3, right? We will have 2 comma 3 in the priority queue and we will finalize the distance of 3 as 2, whether the smallest distance of 3 will be 1, so it will give a wrong answer. So like this, because if we have a negative edge, the node having the smallest distance currently will not have the smallest distance after all the operations are over, right? Like when we are traversing only the neighbors of one, we consider only these two edges. In that case, 3 has the smallest distance of 2. But when you consider this thing also, the minus 2 is coming and it is making the distance of 3 lesser. So this will not work. So here Dijkstra fails. So in that case, we have to use Bellman Ford. So I think we don't have enough time to discuss Bellman Ford, but you can go to CP algorithms and check about Bellman Ford. So Bellman Ford works for negative weights of a graph, provided that there is no negative cycle in a graph. Okay, negative weight cycle. So, but I think Bellman Ford is not very important from the point of view of interviews. Mainly BFS and Dijkstra are most important for the interview purpose. So, because in real life you don't have negative weight, means negative weight edges. So that's why Dijkstra is so popular. Like in Google Maps, also they use Dijkstra, a modified version of Dijkstra, for finding the shortest path and something like that. So that's why DAX is so important for the point of view of interviews. And I think Sonak hasn't joined yet, but I covered both the algorithms. Like we thought about covering these two algorithms today. So any questions on this?
Bhaiya, can you please explain the yeah?
Yeah, yeah. Tell.
Can you please explain the Bellman Ford's intuition once again, because I have disconnected somewhere.
Bellman Ford uses a DP algorithm. Okay. So what it does is that it checks for every pair of vertices. Like means it runs in V cube, I guess. I am not very sure. So what it does here is that, let me just tell you. So if you have a vertex like this, so let's say you have three vertices I, J, and sorry, I and J. So it just checks that if the distance of I is lesser than the distance of J plus the weight between I and J. If it's lesser, it will again start calculating from I, means it will again start calculating the things from I. So it calculates for every edge. Okay. So means it's a means it uses a DP algorithm. So like if you have the distances calculated till I, so you can calculate the distance of J, right? Means it calculates the distance of J from all the sources of let's say if a node J has this many edges, so it will calculate the distance of J from this source and this source, and then it will take the list of that. So it goes like this. So I think in CP algorithms you do have a very good explanation. Like if I try to explain, it will take another half an hour. So I think we don't have so much time. So it does like this. Basically, what it does is that it calculates the number of edges. So let's say you have a graph like this. Okay. So what Bellman Ford does is that in the first iteration, it calculates the distances of those nodes which have a path of length 1. Okay. So let's take an example. Okay. So the let's first calculate the shortest distances from manually. So one has a distance of 0, 2 has -1, 3 has 2, and 4 has -1, right? So the length of path for 4 is 1. So for in the first iteration, the distance of 4 will be updated as 1. Okay. and also 2 will be updated as 1, 3 will be updated as 2, and 1 will be updated as 0. 1 is updated as 0 from the beginning also. Okay, so let's say in the first one 0 is updated and every other thing has infinity. So now since now we will calculate the neighbors of 1. So 4 is the neighbor of 1, so -1 is updated. So now we have 3, 2 is updated, -1, and this is 0. Okay, so observe here is that the nodes which have path of length 1, so 2 has a path of length 1, that is 1 to 2, and 4 has also a path of length 1, that is 1 to 4. Those two have been finalized, right? So now we go to the next iteration. So how we are calculating the iterations here is that when we are calculating for 3, we are taking the distance of 1, and we are also taking the distance of 4, and we are checking that whether if we come from 1 the distance will be lesser, or whether we are coming from 4 the distance will be lesser. So distance of 1 is 0, 0, and the weight is 2, so the total weight will be 2. And if we come from 4, the distance of 4 is -1, and the edge length is 3, so it will be both cases 2. So let's take this as 2. Okay, let's not take 2, 2. So now the distance will be 1 and 2, so we will update here it as 1, right? For 4 also we will check from 3 and 1. So the distance of 3 is 1 and the distance of 1 is 0, so the distances will come as -1 and 3, right? So -1 is lower, so we have taken -1, but since -1 is already there stored in the distance array, we will not update 4 again. So 4 is -1 as it is. Similarly for 2, so like this we go on, we do this for v minus 1 times. V is the number of vertices. Okay, so there is also a limitation of Bellman fort, like you can't have a negative weight cycle. So what do I mean by negative weight cycle is that a cycle which has a sum of weights which is negative, means negative sum of weights. So for example, if we take this cycle, the sum of weights in the cycle is 2 plus 2 plus -1, that is 3, so it's positive, so it will work. But if the sum of the weights is negative, for example, let's say instead of 2 we have -2 here, so now the sum of the weights in the cycle is negative, so Bellman fold will not work. So every time it tries to calculate the distance of 3 from 4 and 1, so the distance of 3 will decrease, right? See, also like this doesn't have a particular answer, because see here, like it will go to an infinity, like 1 3 4 3. If you go on like this, every time you add edges the total sum will decrease, right? Are you getting this point, or is it getting too complex?
Yes, bro.
You are getting or too complex? Hello, like if it's too complex you can tell. Hello. Okay, so basically uh, means from where I should explain again the negative weight, right? Means the negative cycle weight. Okay, so what I'm trying to say here is that if the graph has a means negative cycle, so like let's say take this example 1 2 and -5, so what will be the final distance of 3? Just calculate manually and tell me this first. The minimum distance of 3 starting from 1, just calculate manually and tell me.
-5.
Are you sure? Now let's take this path. What is the length of this path? -5. 2, 1, minus 5. So minus 3, minus 2, minus 5, that is minus 7. So the length of this part is minus 7, right? So minus 5 is wrong. Now is minus 7 the answer?
No, it will go up to infinity.
Yeah, it will go like infinity. Like if we keep on adding 1 and 2 and then 3, it will keep on decreasing. So this graph doesn't have a shortest path. So in this case Bellman fold doesn't work because it doesn't have an answer. So that's what I'm saying. If the cycle has a negative weight, so the cycle here has weights 1, 2 and minus 5, so the total sum is minus 3. So if such a cycle exists, so there is no answer. In that case Bellman fold will not work. Okay, so this is how Bellman fold works. But I think Bellman fold is not very useful for the point of view of interviews because it doesn't really have a real life implementation. Okay, so any questions on this or we can end?
So bhaiya, there will be only BFS, DFS, 01 BFS, and Diestra. These
Yeah,
four algorithms
mainly.
are
Yeah, this four will be used mainly. If you know how to use this four algorithms, you means you are good to go. Like even I also use this four algorithms mainly. Like I haven't used Bellman fold in my entire DSL life. Only for practice or solving problems only I have used, but in contest or in interviews I have never used Bellman fold.
okay.
So like for graph, you should know BFS, 01 BFS, Dijkstra, DFS, and DSU maybe like the number of connected components that can be done by DFS also. So these four are enough. Like if you do this four well, you are good to go. These four are more than enough basically. For internship, you also will not be asked Dijkstra. Dijkstra is asked mainly for full-time interviews. Okay, so but just for the safety purposes, you just means practice Dijkstra. Just
Bhaiya,
practice those four:
will,
01
will,
BFS, BFS, Dijkstra,
will
and
we
DFS
receive any assignment on this graph?
from college.
No, no. Will we receive any assignment on this graph?
Yeah, I
Means
think there will be 4 questions on 4 algorithms. That will be the last assignment for this thing. Okay.
okay, bhaiya, thank you.
So any other questions or we can end here, I guess. So I will wait for a minute and then end. So any feedback regarding this spring of competitive programming for the next year? How we can improve? Like just we will float a feedback form and you should fill this up because in the beginning we saw there are around 30 to 40 participants, but in the last few sessions we have only 8 or 10 participants. So so just fill the feedback form that how we can improve, like we could have more participants in the future year or future sessions. Okay, so we will be giving a feedback form and just fill those up. So any other questions or I think we can end here, like. So I think nobody has any other questions. So okay, so bye everyone.